Okay, so let's have a look at using the Go language to implement some basic elliptic curve methods. Okay, so let's do some of the basics behind elliptic curve. So the equation that we have for elliptic curve is something like this. And within our elliptic curve methods, we also have a mod of a prime number. So this equation here looks a bit like this when we draw it. And the values of A and B will actually define the shape of the elliptic curve. What we do is that we take a point on the elliptic curve, let's call that G, and then if we add that point onto itself, it will create another point on the elliptic curve. So we'll just try that. So then that will be G plus G. And then if we add that point again, it will also give us a point on the elliptic curve. So no matter how many times we actually add the points, we always get a point on the elliptic curve. So what we do within our public key encryption, so with public key encryption, Bob has a public key and a private key. The private key he keeps secret, and he can release the public key to anyone who wants to prove his identity. So what he typically will do is to sign things, encrypt things with his private key, and then will prove that he signed something with his public key. So with elliptic curve cryptography, what we do is that we take a base point. This is called the G. So this is Gx and Gy. We then take a random number and that becomes our private key, or N in this case. Then we add G n times, so basically comes G plus G plus G and so on until we add it n times. That then gives us a point on the elliptic curve called P, and we represent that as P is equal to n times G, or adding G n times. This becomes our public key, and this is our private key. And at present, computationally, even though we know this value, that's a point xy, and this value, we cannot determine this value in here. Okay, so that's the basics that we have for elliptic curve cryptography. So the key elements that actually define our elliptic curve, the key parameters that define them, and we'll just redraw our curve again. Okay, so there's our curve. So the curve is y squared is equal to x cubed plus ax plus b. So we have various types of curves, and the parameters that we have is the prime number p, and that's defined as the order of the curve. And so all our operations are done with a mod of p. We then have n, which is the order of the base points. Okay, so we have a point G, and we have a G of X and G of Y, which is our base point on the elliptic curve. And then in the NIST standards, the value of A is 0, so we end up with a B value. So the B value is actually defined for the elliptic curve type that we have. So it's these basic parameters which are used to define the elliptic curve. And we'll see those parameters in a little minute. So what are the basic methods that we use for our elliptic curve? Well, we start with our base point. So let's say here is our base point here. G. It's a G of X and a G of Y. So the basic method that we have is to do what's called a scalar multiply. So the scalar multiply takes a value of n and finds a point P. So we do a method, if this is a curve C, we do curve dot scalar multiply, and we take the X point and the Y point, and we take the n value, and this method will return this. We can also do a method called scalar base multiply, and automatically from the curve it will take the G of X and G of Y, and so all we need to do is define the n value here. So the first one is used when we have any point on the elliptic curve. We might take any point that we want, such as when we're hashing a value onto the elliptic curve, say our password. We could use the scalar multiply to be able to take any point and then multiply it to find a public key, say. The scalar base multiply method is used to automatically take the base point and multiply that by our value of n there. So that's the scalar multiply. So we take our point and we multiply it by our value, typically with our private key. Another thing that we do often is that we add 2 points together. So we might have a point here and another point there, and when we add them together we'll get another point on the elliptic curve. So the great thing with elliptic curve is that we take one point and add it to another, we'll find that our elliptic curve point is on the elliptic curve. So with that, we will say that P, there's P there, and we'll take a point G1 and G2 to give us P. So P is equal to G1 plus G2. So the method we use with this is add. So we would add our points, so we can either add our G of X, G of Y, and take the next point, or we can add these as points. So this is another useful method that we have. Takes two elliptic curve points and add them together, and we'll get a result. The thing about this is that even though we know P, it is actually extremely difficult to find the 2 points which made up P. So the add method is useful for us. The other one that we have is what's called double. So often if we want to compute a a scalar value of a point, we double, 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 and so on, and that allows us to be able to very quickly determine the answer. So if we want to take a point and double it, okay, then we use a method c.double, and we'll take our x point and our y point, and it'll create a doubling effect. And this way we can very quickly double, 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 and so on. So every time we double, so that's 4, 8, 16, and so on, we can increase rather than adding 16 times. We can very quickly double, double, double up, and it will allow us to very quickly create our multiplier, and with this double method. Okay, so I'll just recap what we've just shown there. So the core method that we have is the scalar multiply, we have the scalar base multiply, we have the add, and we have double. Scalar multiply will take any point that we want and then multiply it by a certain value to give us another point on the elliptic curve. The scalar base multiply will take the base point. We don't have to specify it because we've specified it with the type, and then we can multiply that by a certain scalar value. Add will add 2 points, elliptic curve points, together to give us a result, and double will take the same point and double it. The last method that we need gives us a basic check, is on curve. And with this is a Boolean function where we pass the x and y point, and it tells us true if it's on the curve and false if it is not on the curve. Okay, so that's the core methods that we use for elliptic curve cryptography with Go. So here we go. This is our program here. So I'll show you the program in a minute. We're going to grab the parameters for the curve that we specify, and we're going to display the b value, g of x, g of y, and n, and so on. Then what we'll do is we'll generate a 256-bit random number here. That's going to be our scalar. We'll then take our base point. So rather than scalar base multiply, I'll just use scalar multiply and take the g and the x value there for our curve, and we'll multiply it by a scalar r to give us our public key, or p value. So this is the equivalent of saying p is equal to n, or in this case r times g. We'll display that out, and then we'll test to see if that point here is on the elliptic curve. If it is, and it should be, then that will return a true. Now what we'll do is that we'll calculate another point. Let's say r1 times g, and again we'll generate a public key point for that one here. And next what we'll do is that we'll add the 2 public key points together to give us another point, p3, and we use this method here, and again we'll check to see if it's on the curve, and hopefully it is, because 2 elliptic curve points when added together should end up on the curve. And then finally we'll do a double of the original public key point, print it out, and then we'll just test to see if that is on the elliptic curve. So that's our core Go program, and what we'll use is the NIST curves that have been defined for us. So I'll have a quick look at how that program actually runs. So here we are here. So for the NIST 2 to 4, we can see the parameters. There's the prime number that's used. There's the b value. Remember, it's x squared, y squared is equal to x cubed plus this value here. And then there is the base point that we're using for the curve. Next, we generate a random number for our private key and calculate the public key point. And then we check to see if that's on the elliptic curve, which it is. We generate another point and add the points together to give us this one. Again, we check to see if the resultant point is on the elliptic curve, and it is. Finally, we take our original public key point and we double it, and again we check to see that it's on the public key, it's on the elliptic curve, and it is. So we can do this for other curves. So this is 256. You can see that the prime number is larger, it's more secure. And there's the 384, and there's the 521. That's the most secure point. Okay, so in Go, this is how we specify the methods that are coming in, and this is just defining the curve here, which we then take the parameters from there. Okay, so that shows how our Go program actually works. So we just have a quick look to see what the output is. So this is it again. So there is the prime number. There is the b value. Here is the g point. We have our private key, and this point here is equal to n times g, which is this here, and our n value is there. So this gives us our public key here. Check to see if it's on the curve. Next, we'll take another random value and we'll create another public key point, and then we'll add them together here to give us this output. Again, we check to see if it's on the elliptic curve, and it is. And finally, we'll double the point, public key point that we created, to give this, and the value is true. Remember, we're using a mod of a prime number all the time, so it's not just a calculation where we double the value and so on. Okay, so that gives you an overview of the elliptic curve and Go.